All right, we're back. Go ahead and read it. We're there. I don't know if that helps. Good. Okay. All right. So the study in question is focused on student population at Cal Poly with the aim of understanding preferences for two products designed to bolster school spirit: a uniquely branded hat and a series of collectible stickers. The entire student body at Cal Poly formed the population for the study. However, the sample that we have access to for this study is limited to 75 students from business class. We have our population, we have our sample, we have our observation unit. Okay. The statistical question being explored is whether the proportion of Cal Poly students who wear hats, given that they do not collect stickers, is the same as the proportion of Cal Poly students who wear hats, given they do collect stickers. In other words, we are comparing two groups of Cal Poly students: those who collect stickers and those that do not. Interesting. We want to know if the likelihood of wearing a hat is the same for both groups. This will help us understand student preferences and perceptions regarding these products to ensure they resonate well with the campus community. The hat is stylish, versatile. It's perfect for both casual wear and sporting events. Wow. The stickers offer a fun and personalized way for students to decorate their belongings, reflecting their individuality and school spirit. Our goal is to ensure that these products are well received and cherished school symbols of pride and unity within the Cal Poly community. That rhymed. All right, so SSVA, Summary Statistics Visualization Analysis. Go ahead and check out the numbers. All right, so here is a contingency table that allows us to see the frequency of these two variables: if they wear a hat or if they don't wear a hat, and then those that collect stickers that don't collect stickers. Okay, versus those that don't collect stickers. That's that. So this question is you have to do a little bit of work to get what we're after. So this statistical technique is two independent population proportions test, which is a proportion. So therefore we're dealing with categorical variables. Okay, so just be aware of that. But calculating the proportions takes a little thought, so we'll come back to that in a moment. Visually speaking, if we're dealing with categorical variables, we should use a bar plot to visualize our data. So we have essentially the same information here as for our summary statistics here in our visualization. Okay, as you can see, a lot of people do not collect stickers. Okay, no. I did that right. Yeah, a lot more people do not collect stickers. Okay. We want to see if the proportion of those that do wear hats. Where is it? I'm going to read it again. So, those that collect stickers versus those that don't collect stickers are the same for those that wear hats versus those that do not wear hats. No and yes. Okay. And then here are the relevant statistics. I calculate the proportions for you. So you give the frequency, you give the proportions that you're after: 30 over 58, 12 over 17. Those are the individuals, 30, those that collect hats for both groups over those versus those that collect stickers versus don't collect stickers. These are the proportions. These are the difference between the proportions. This is the calculation of standard error for confidence intervals for those proportions. And we have the confidence level and the critical value, lower bound, upper bound. Exactly what I'm looking for. The standard errors for the hypothesis test for that difference between the population proportions. Sample proportions. Okay, so that's that. It's different. You're gonna see in a little bit. These equations are different for confidence intervals versus hypothesis testing. All right, so take a moment and answer these questions. Thank you. All right, not even pause it this time. It's fine. Okay, third video of the day, something like that. What would be the population of interest? All Cal Poly students. Describe the sample at hand is going to be the 75 business students, and observation is going to be a Cal Poly student. Okay, what is the response variable? The response variable is going to be whether they wear a hat or not. Whether they wear a hat, the explanatory variable is going to be if they collect stickers. Explanatory variable is going to be if they collect stickers, okay? And so it collects both of those variables are categorical binary. Let's see if I get that right. So response variable is if they wear a hat or not. Yes. And then stickers is the explanatory variable, and both of them are categorical binary. Okay. All right. So the research question is if the explanatory variable, if someone collects stickers or not, has an impact on them wearing a hat. Okay. And so, how do I say that? Is the proportion of Cal Poly students who wear hats, given that they do not collect stickers, the same as the proportion of Cal Poly students who wear hats, given that they do not collect stickers? Okay. The statistical technique at hand is going to be the two independent population proportions test, and we can answer this question using the hypothesis test or a confidence interval. Actually, this video series, both of those techniques, paired t-test and the two independent population means test, pooled or Welch's, you can answer the question using confidence interval or hypothesis test. All right. So state the parameter of interest using symbols. Not words. Interesting. So it's going to be the proportion. Oh, just state it, not just. Okay, that makes sense. P1 minus P2, where one is wearing hats. Both of them wearing hats, but one is giving no stickers and two is giving no stickers. And you want to see if it's equal to 0. Okay, you want to see if that proportion, or these two proportions are the same. That's why you're testing for it to be equal to 0. Okay, and then the statistic is going to be just the P1 hat minus P2 hat. Okay, and so that's going to be the difference in proportions, which is negative 0.1886, and that shouldn't be a surprise because that is our difference here. Okay. All right, so then this is going to be the sample proportion. It's the same thing, but it's the sample proportion of Cal Poly students who wear hats, given that they do not collect stickers, is the same as the sample proportion of Cal Poly students who wear hats, given they do collect stickers. Okay? So when implementing two independent population proportion tests, what is the difference between hypothesis testing standard error versus confidence interval standard error? I'll let you read this on your own, but the equations are a tad bit different. For hypothesis testing, you're pulling in your proportion, okay, in which you're looking at the number of successes for both groups divided by the sample size. So you're going to add 30 plus 12 divided by 75. That's what's going to be your PC. And then for standard error for confidence intervals, they're separated. It's done separately. Okay, so you should practice doing this to confirm the answers that are given in your our output. Okay, so you have that for hypothesis testing, and you have this for confidence intervals. Okay, and the reason for why you would even want to do something like that is because when you are doing hypothesis testing, I believe it definitely says this here, is that you're assuming that the null hypothesis is true. So if the null hypothesis is true, it's going to be just one proportion. Whereas for a confidence interval, you're not making that assumption. You're just seeing if they're what the actual proportions, the range of plausible values for the difference in population proportions. So that's why it's separate for confidence intervals. Hopefully that makes sense. That's a lot. It connects back to two independent population means. Okay, but ask me questions during learning hours for further assistance. Okay, so in summary, this does a good job of it. In summary, the difference between standard error, hypothesis testing standard error, confidence interval lies in the assumption about the population proportions and the way they're calculated. Okay, again, for hypothesis testing, we're assuming the population proportions are equal. Okay, whereas for confidence intervals, we're not making that assumption. All right, so for hypothesis testing, say the non-alternative hypotheses. The nulls of the population proportions are the same. The alternatives of the population proportions are different. However, utilizing symbols, it will look something like this. This is the null. Okay, where 1 is equal to one group and 2 is equal to the other. And then in words, the population proportion, let you read that on your own. And the alternative hypothesis is that the difference between the population proportions is not equal to 0. And again, the words are the same. The only thing that's different here is that the not between the null and alternative. Okay. In terms of assumptions, we need to check that n time for hypothesis testing. N times 1 is greater than or equal to 10. N times Q1, which is 1 minus P1, is greater than or equal to 10. So you'll do that 75. So at the end of the day, what you're really just checking is all 4 quadrants, while it's a lot of scrolling, all 4 quadrants of the contingency table are all greater than or equal to 10. This is not. So therefore, you would still continue the test, but be wary of your results. Still continue the test, but be wary of your result. Okay. Because we're doing proportions, we would utilize the z distribution. From the first time I'm mentioning z distribution. The normal distribution, normal and z are the same. We'll use this distribution to figure out the likelihood of our test statistic. Okay, so keep that in the back of your mind. Okay. And we're always going to use a normal distribution. Okay. Whereas, and my apologies for not emphasizing this earlier, the other assumption is that there's some randomization in terms of sampling. So that n times p, n times q, 1 and q2, p1 and p2 greater than or equal to 10. That's an assumption. These are assumptions. And then randomization of sampling is the second assumption. Okay. Calculate the test statistic. This equation is gnarly. Okay. Well, it's not too bad. Just the difference between the proportions divided by standard error hypothesis testing. The hypothesis test, standard error, you should double check it. Make sure you can get those numbers. But it's, once you plug this into the test statistic equation, you get negative 1.377. This answer is actually found in our output. Okay, note that as well. You'll be given enough to answer questions on the test, or sorry, the quiz. All right, so here in terms of our test statistic, you would write, it would be over here to the left. Okay, it will be somewhere around here, and this will be the p-value to the left. Okay, so the vertical line would have been the test statistic. Let's make this a different color. I guess I can't do that. I can. I'm pretty sure I can. All right, well, the vertical line is the test statistic, and the area underneath the curve to the left would be the p-value. Since the test statistic is greater than, no, it's not, is not greater than negative 3.5, we do not have, this is not true. We do not have evidence. We don't have, we need a p-value. So I'm just going to cross this out. So you all don't have this in your answer key. The p-value is given to us, and they'll always be given to you in some way, shape, or fashion. Oh, look at that. The p-value is large. Okay, so that means that we should do what to our null hypothesis? Since greater than 0.1, we should fail to reject it. That's interesting. Okay. I guess anything can happen. Since the p-value is greater than 0.1, we will fail to reject the null hypothesis. Okay, that's fine. Okay, state the point estimate, calculate 95% confidence interval, use 1.96 as your critical value. What assumptions need to be met? Okay, the assumptions are a tad bit different for confidence intervals. The logic still works the same. The point estimate is just the difference between the sample proportions. Point estimate plus or minus critical value. Standard error was given to you. The critical value was given to you. Standard error, you can confirm this again on your own time. And notice that our lower bound is negative 0.44. Our upper bound is positive 0.06. Based on that, it's plausible for the difference between the population proportions to be 0 based on this interval. So these results, us deciding to fail to reject the null hypothesis and our confidence interval, including 0, agree with one another. Okay, think about that for a little bit. Okay, the confidence intervals results agree with the results for the hypothesis test, which should make sense, indicating that the population proportions based on data are the same. Okay, so regardless of wearing collecting stickers or not collecting stickers, you wear a hat, you wear a Cal Poly hat. And this is real data, which is kind of cool. We are 95% confident. That's how you interpret the interval. We are 95% confident that the difference between the population proportion of cowpox students who wear hats, given that they do not collect stickers, and the population proportion of cowpox students who wear hats, given they do collect stickers, is in between negative 0.44 and 0.06. What are the implications of 0 within the lower bound, upper bound? Since 0 is within the lower bound, upper bound for the difference between the population proportion of cowpox students who wear hats, given that they do not collect stickers, and the population proportion of cowpox students who wear hats, given that they do collect stickers, it is plausible that there is no difference between these two population proportions based on the data. Based on the data. Okay? So how hard was that? Okay. Well, take a moment, look over the review. There's some review questions. It's a lot of material. Let me know if you have any questions, and ta-da!